The mushroom cloud. High energy explosives and the mushroom clouds that they create are byproducts of our desire to destroy. Given it's provided enough energy, the mushroom cloud is formed when a bomb provides the energy needed to heat surrounding air hot enough for the ball to rise. Once risen, this sudden updraft, along with the dust that follows, produces a stem. Finally, after the fireball has reached a certain point, it will begin to cool, causing vaporous materials contained within to condense and spread, finalizing our mushroom shape. The evaluation of a mushroom cloud branches together many sciences, with people regularly studying the kinetics, chemistry, and physics of these phenomena. We decided to focus in on determining the necessary energy released by an explosion based on radius, time, and density properties. Our idea is that different size blasts will produce different size radiuses, as well as different density materials will travel at different speeds after detonation. And lastly, time can be used to gather a frame of reference. In all, we'll be able to solve for the energy produced by a specific bomb.
As our mechanism focuses on many different physical properties, it was decided that for the analysis we were going to calculate the energy necessary to generate a mushroom cloud of a determinate radius. To do so, we used the concept that energy will be a function of radius, time, and density, and perform a dimensional analysis to generate the appropriate equation. To begin solving the problem, we have to assume that the shock wave generated by the explosion is spherical, and the energy was released in a small space. First, we define our variables in the MLT system: E for energy released by the explosion, R as radius of shock wave, T as time, and rho as density. Next, we define our energy function: E equals F of R, T, and rho. Then we define our repeating variables, which are R, T, and rho. Subsequently, we calculated the number of pi terms. Because we have 4 variables and we are using the MLT systems, we are going to have 1 pi term. After this, we follow by solving our pi terms. Pi equals E times R to the A times T to the B times rho to the C. Substituting each variable for its dimensions and solving for each letter M, L, and T, we'll get that C equals -1, A equals -5, and B will equal 2. Plugging back to our pi term, we will get that pi equals E times T squared over R to the 5 times rho. Pi will be assumed as a constant and will be equal to 5, therefore our energy equations will equal R to the 5 times rho divided by time squared. Now we're going to show you a video clip of SpongeBob SquarePants and we're going to analyze it.
Let's eat! Oops!
Following this introduction and the leading theory that Bikini Bottom is only 6 feet underwater, we're going to use the size of a small anchor for the radius. We're going to use the density of water at 15.6 Celsius and a determinate time to calculate the energy released by the explosion. After doing this calculation, we get that the energy released was 119.74 kilojoules. Based on that 1 kilojoule equals 0.24 grams of TNT, we will need about 28.62 grams of TNT to replicate the mushroom cloud portrayed in this episode.
After a series of failed analyses, we decided to go with our dimensional analysis, previously learned in class. We believe that based on our calculations, we are able to prove that our observation makes sense as energy will vary as a function of time, radius, and density. Hopefully, we're able to have a little fun while doing so. Thanks for listening.